afternoon. So in today's lecture, we are going to take the path of the final escape route from Arrow's impossibility theorem. And the idea here is similar to the one on the last escape route, where we looked at these impossibility theorems, and then we focused on expansion consistency conditions, because contraction consistency was prohibitive for social choice. And then we only took an expansion consistency condition like beta plus or gamma, and then even weaker conditions like rho plus, and completely characterized attractive social choice functions using these conditions. And on the fourth escape route, the idea is a little bit similar in the sense that we're also looking at these consistency conditions, but rather than only weakening expansion consistency, we are defining a new weakening or a new type of consistency condition, which is weakening both expansion and contraction. And that will lead us to a couple of different social choice functions, but we are only discussing one single one in this lecture. So this lecture will be completely devoted to a single majoritarian social choice function called the Bipartisan Set. And so now by now you have seen quite a number of majoritarian social choice functions: Copeland's rule, top cycle, uncovered set, bank set, tournament equilibrium set. And the Bipartisan Set, at least in my mind, can be considered something like the holy grail of majoritarian social choice functions. So it's definitely something to look forward to. There's some maybe slightly more complicated mathematics involved in that, but I think it's worth it because it's really an interesting social choice function. Okay, so that's the rough outline of today's lecture. But before we talk about the Bipartisan Set, let me introduce this general escape route from Arrow's impossibility. And the basic idea is as follows. So the point of departure for this new escape route is that choice functions and also social choice functions yield sets of alternatives. Okay, so that is how we defined a choice function. However, these conditions that we studied in the second lecture, rationality and consistency, are based on the alternatives themselves. So, for example, a rationalizing relation is a rationalizing relation on the alternatives and not on sets of alternatives. Or similarly, if you take consistency conditions like alpha and gamma, these are also defined in terms of alternatives. So, for instance, alpha and gamma, the conjunction of alpha and gamma is just a statement that an alternative at the intersection of two feasible sets is chosen in both feasible sets if and only if it is chosen in the union of these sets. Okay, but these are statements about alternatives rather than sets. And the idea for this escape route is to redefine these conditions, so both rationalizability and conditions like alpha and gamma, in terms of sets. So for instance, for rationalizability, we are going to define a version of rationalizability where we have a relation on sets. And for alpha and gamma, we will also have conditions that are based on sets rather than single alternatives. So this is the underlying idea. So we are now going back to the very roots of this entire lecture, where we started with choice theory. So I hope you do remember at least a little bit on how these conditions were defined and what the idea of rationalizability was. In case you don't, so I'm going to repeat some of these. So I hope you will be able to follow everything here. So the first thing that we are defining is a set-based notion of rationalizability. And this is defined as follows. So we say that a choice function is set-rationalizable if there exists some binary relation on sets of alternatives. So this is the main difference now, that this relation here is defined not on u times u, but on f of u times f of u. So f of u is the set of non-empty finite sets, non-empty finite subsets of u. So we have a preference relation on sets of alternatives. Okay, and then we say that a choice function is rationalizable if for every two feasible sets A and X, X is chosen from A, if and only if X is maximal according to this relation on sets of alternatives. Okay, so the idea is this is almost the same definition that we had for rationalizability, except that for the standard notion of rationalizability, this relation was defined on alternatives, just u times u here. And then we said that an alternative little x was an element of the choice set if and only if x was a maximal element according to this relation. So the underlying idea is similar. So we want to rationalize behavior in the sense that a choice function seems rational if there's an underlying relation now on sets of alternatives such that a maximal set will be returned. So one thing that you can already see here is that, of course, we can only return one set, right? If you're talking about alternatives, we can say that several alternatives are returned, but a choice function always returns a single set. So alternatively, rather than writing that X is a maximal element, I could have also written that the set of maximal elements only consists of the singleton of the set that only consists of X, right? So because we can only return a single set from every feasible set. But otherwise, especially syntactically, the definition is very similar to what we had for the standard notion of rationalizability. Okay. So similar to the base relation that we had in choice theory, we can also define a set-based base relation. And we define it as follows. So we are saying that, okay, that's not very nice. We are saying that the base relation, so which is again the symbol here with the subscript s as it used to be, we are basically extending this to sets of alternatives by saying that one set is weakly preferred to another set if and only if the first set is chosen from the feasible set that consists of the union of x and y. Okay, so if you think about the standard base relation, we just said that x is weakly preferred to y if x is chosen in the presence of y. In particular, or specifically only from the two-element set x, y. And here we are defining something similar for sets. So the set x is chosen, the set x is preferred to the set y if the set x is precisely the choice set from the union of x and y. Okay, so it's not very difficult to see that this extended base relation is not complete because well, the standard base relation for social choice, for choice theory was complete because well, from any two-element set we had to choose something. But here, of course, it doesn't have to be the case that x or y are chosen from the union of x and y. It could be that there's a completely different set which is chosen from x union y. So therefore, it doesn't have to be the case that this relation is complete. The relation is anti-symmetric. Okay, so it's impossible that x is weakly preferred to y and y is weakly preferred to x if these are two different sets, clearly, right? Because, well, either x is the choice set or y is the choice set, but not both of them at the same time. And to get some more insight, let's look at a concrete example, because usually once you think about preference relations over sets of alternatives, it seems a bit abstract, and I hope that once you see an example like this one here, you get some more intuition into this. Okay, so this here is a simple choice function. We have like a universe of three alternatives. From A, B, we are choosing A. From B, C, we are choosing B. From A, C, we are choosing C. And from the set of all three alternatives, A, B, C, we are choosing A, B, C. Okay, and now based on this choice function, we can now draw the base relation, or the extended base relation, denoted by this symbol here. So what I'm drawing here is really just this relation here. And let's just see how this works. So first, the number of different non-empty subsets here is 7, because we have three alternatives and there are 7 non-empty subsets, so we always have to choose something. And then, for instance, look at maybe those little loops here. So from the singleton set A, we are choosing A. Okay, so this is not specified in the table here because it's trivial. That's why we have these loops here. So if you look at this definition here, so we have to have a weak preference from A to itself, and the same is true for both of the other singleton sets. And then, for instance, if we look at the feasible set AB, then it turns out that from AB, A is chosen. So therefore, according to this definition here, we have an arrow from A to AB, right? Because the one element set A is chosen from the set AB union A, which is just AB. So therefore, we have an arrow from here to here. And similarly, from BC, B is chosen. From AC, C is chosen. And then we have the set of all three alternatives here. And there it turns out that from the set of all three alternatives, ABC, ABC is chosen in this choice function here. And that means that ABC has an arrow pointing to all of the other subsets of ABC, right? Because only ABC is chosen. So that is precisely the choice set from the feasible set ABC. And that's why we have all these outgoing edges, including a loop, of course, because ABC is chosen from the feasible set ABC. Okay, so first thing to realize if you look at this example is that, well, this is the base relation here, and this base relation rationalizes this choice function. Okay, because in every feasible set, so if we, for instance, look at the set of all alternatives ABC, well, then we have an undominated alternative. Here it would be ABC because nothing nothing is dominating this set according to this relation here. So ABC is chosen from the set of all three alternatives ABC. If we, for instance, look at the two-element set AB, okay, so then the possible subsets of AB would be AB, singleton A, singleton B, and A is the unique maximal element according to the relation restricted to those three subsets. So for every possible subset here, we have a maximal element. And this is noteworthy because if you think about this choice function in terms of the classic notion of rationalizability, we observed that this choice function is not rationalizable according to the classic notion, because that's basically the Condorcet paradox. Right, so from AB we choose A, from BC B, from AC C. So that basically can occur if we look at cyclical majorities. And then no matter what we choose from the larger set ABC, just because of these choices here, this function will not be rationalizable in the classic sense of rationalizability. But according to this definition of set rationalizability, it turns out that this extended base relation rationalizes this choice function. Okay, so this is just to give you some idea that according to this modified definition of rationalizability called set rationalizability, we can have a choice function which is not rationalizable in the classic sense, but it is set rationalizable according to this new definition here. Okay. And now, similar to this notion of set rationalizability, we are also going to introduce variants of contraction and expansion for sets. So this alpha and gamma condition in particular. So we're not looking at other conditions like beta plus or rho plus or something that we had before, only alpha and gamma. And now if we first look at the classic conditions here, alpha and gamma. So there was one slide many weeks ago in the second lecture where I found this or presented this nice way of stating alpha and gamma such that they are really dual to each other. And if you recall, it was the following condition here. So we had two feasible sets, A and B, and some alternative x at the intersection of A and B. And then alpha says, if x is chosen from the union of A and B, then x is also chosen from A and is also chosen from B. And gamma says, if x is chosen from A and from B, then x also needs to be chosen from the union of A and B. Okay, so one direction. So you can see these are two implications, and you can write them as an if and only if, and then one direction would be alpha and the other one would be gamma. And now the set versions of alpha and gamma are quite similar in the sense that we also have two different feasible sets, A and B. But now rather than having an alternative x at the intersection, we have a set of alternatives, which is a subset of the intersection of A and B. So just like in the figure here, so we have some set of alternatives x. And then this set variant of alpha, which we denote by putting a little hat on top of alpha. So this condition I will refer to as alpha hat, and this one is gamma hat. So alpha hat says that if x is precisely the choice set from A union B, then x is also the choice set from the feasible set A and from the feasible set B. Okay, so you can, even syntactically, you can see that this is really exactly what you would expect if you transfer this to sets of alternatives. And the same can be done for the gamma condition, where we are saying that if x is precisely the choice set from this feasible set and from that feasible set, then x is also the choice set from the union of A and B. Okay, so at this point, I'm just like redefining those conditions by making reference to sets of alternatives rather than just the alternatives themselves. So basically what we have done here, we have replaced x element with capital X equals. Okay, so at this point I hope it's clear that these are well-defined conditions. So one thing that is important to realize, and I think that's also an upcoming exercise, so despite that these conditions look similar to the traditional ones, there are no logical relationships between them. So alpha doesn't imply alpha hat, and alpha hat doesn't imply alpha, and gamma doesn't imply gamma hat, and the other way around. So you can prove this by coming up with examples. So we didn't do it for the exercise completely exhaustively. I think you only need to do it for alpha and alpha hat, I think, in the exercises. But you can trust me on the fact that also gamma doesn't imply gamma hat. Okay, so these are the definitions here. So one statement that allows us to really work with in particular alpha hat in a nicer way is to show that it's equivalent to another condition here, which I'm stating here below. So basically the main reason for defining alpha hat as it is defined here was just that you can see the analogy to the traditional alpha condition and also how it's related to the gamma hat condition. But I will now claim that this alpha hat condition is actually equivalent to this condition here, which is very natural. So for this condition, we have two feasible sets. Let's call them V and W to not use A and B again. And then what this says is that if what we are choosing from V is a subset of W, and W at the same time is also a subset of V, then the choice sets from V and W are the same. Okay, so I think it usually helps if you, for all these consistency conditions, to really draw a figure to see what's happening here. So we have three sets that are contained in each other, right? So the largest one is the set V. Then we have W. And this one here is what is chosen from V. Yeah, so this always becomes a bit ugly because I cannot zoom in here using Keynote. Okay, but anyways, so these are the three sets that are nested into each other, and then the implication of the statement here is that whatever was chosen from V is exactly the same set that is chosen from W. Okay, in other words, what that means, because these sets are nested in each other, so we have a set of alternatives, and then we have a choice set, and then we are getting rid of unchosen alternatives. We are just removing them. Only unchosen ones, because of this condition here. Okay, and if we are removing unchosen alternatives, then the choice set is not affected. That, I think, intuitively seems like a reasonable condition, because if some alternative which is not winning anyway is just removed from the potential set of options, then this should not affect the choice set at all. Okay, and I say that this condition is exactly the same as the alpha hat condition that is stated here. So maybe to first see the direction from left to right, for instance. Okay, so because here you can already see that this condition, you don't really need both of these implications here. So here we are saying that if X is chosen from the union of A and B, then X is also chosen from A as well as from B. Okay, nobody said that we cannot have A and B included in each other, just like for this condition here, and then we directly get this condition here, right? So if B is a subset of A in this statement here, then we have precisely this statement here. Okay, so that's already proves the direction from left to right. Oh, let me write it down. Basically, yeah, so for the direction from left to right, we just have that V equals A and W equals B. Okay, and if you do it in the other direction, okay, so here I actually have specified the proof. So for the direction from left to right, we just need to use this fact here. And if we go for the other direction, that means we have this condition here and want to show that alpha hat has to hold. Basically what we are doing is just that we are defining X wait a second. For the other direction, we have that V is A union B, and W is just A. Okay, and then we can use this statement here and get that whatever is chosen from A union B is a subset of A, which in turn, of course, is a subset of A union B, because A is always a subset of A union B. And then we get as a consequence that the choice sets of A union B and S of A are the same. And then since alpha hat has two consequences, we now prove this one here, we also have to show the other one. And for the other one, we again use V is A union B, and then W is just B. Okay, because this alpha hat condition as it is written up here has two symmetric consequences. And we get both of these by applying this condition twice. Once where V is A union B and W is A, and once where V is defined as before, A union B, and W is just B. Okay, so it's, as I said, so I mainly wrote down the alpha hat condition like this here to see the analogy to the other conditions, but whenever we are working now with alpha hat, we will really just have this very intuitive definition, because both of them are equivalent here, which says that if we are deleting unchosen alternatives, then the choice set is not affected. It will remain exactly the same. Okay. So, now one question that you might ask yourself, how are these conditions related to each other, consistency and rationalizability? So in the second lecture, we had this classic theorem by Zen, which said that choice function is rationalizable if and only if it satisfies alpha and gamma. In the case of set rationalizability, it turns out that we only need alpha hat. So a choice function is set rationalizable if and only if it satisfies alpha hat. And that's again a very useful statement, just like the statement that we had in the second lecture, because as you have seen in the example before, where we checked the base relation and then we checked whether this base relation rationalizes the choice function. Now the base relation, or the extended base relation for sets, operates on a much larger set, because, well, there are of course plenty of subsets, and it becomes even more difficult to check whether a function is rationalizable or set rationalizable. And this statement here allows us to just check set rationalizability by only checking whether alpha hat is satisfied. So if you, for instance, think back about the example where we were choosing ABC from the set of all three alternatives ABC, and then we had certain choices from these two element sets. So clearly this satisfies alpha hat, because the only interesting case where alpha hat needs to be verified is for the set of all three alternatives where all three ABC are chosen. So deleting unchosen alternatives doesn't affect the choice set, but there are no unchosen alternatives. So alpha hat is trivially satisfied for this choice function. But in general, it's quite convenient to use this statement in order to simply check whether a function is set rationalizable or not. Showing this equivalence is not particularly difficult, so that's why it's an upcoming exercise, but I think it is a tutorial exercise. So you don't need to worry about that too much, because you will see the proof in the tutorials. Now, so this slide is headed stability, because there's one other property that I'm going to define, and that is the notion of stability. And we are just saying that a choice function is stable if it satisfies both alpha hat and gamma hat. Okay, so this is just, so you can think of this as another word for alpha hat and gamma hat. And the reason why we are doing this is because for set rationalizability, as this theorem there shows, we only need alpha hat, but nevertheless, gamma hat seems like a very desirable additional condition to have for choice functions. Because if you recall, so alpha hat just means that deleting unchosen alternatives doesn't affect the choice set, whereas gamma hat means if the set X is chosen from one feasible set and from another feasible set, then it should also be precisely the choice set from the union of these two feasible sets. So these two conditions together seem like a very reasonable desideratum for choice functions. Whether these conditions can be easily satisfied is a different question. So I can already reveal at this point that there are not many functions that satisfy any of these conditions, but it seems interesting to precisely look for those functions that do satisfy the conditions. Now, let's make clear exactly why we are now on an escape from Arrow's impossibility, because I said earlier that alpha and alpha hat and gamma hat are not logically related to each other. So at this point, it's not clear whether this is really weakening any of the Arrowian conditions. Therefore, you need this following statement here. That's basically like could be the theorem or proposition, because, well, it needs to be proven. It's not obvious that this is the case, but It is. So a choice function is quasi-transitively rationalizable if and only if it satisfies alpha, alpha hat, and gamma hat. Okay, so now we take two of these set conditions, alpha hat and gamma hat, and we add this rather strong alpha condition, because we have seen before that alpha is really the main condition that prevents social choice, and all three conditions taken together are precisely quasi-transitive rationalizability. And therefore, it's obvious how this defines an escape route from Arrow's impossibility. Because if you think back about those classic conditions that we studied at the beginning of the course, we had these three different notions of rationalizability. And transitive rationalizability was equivalent to a condition called warp, the weak axiom of revealed preference, which again was equivalent to alpha and beta plus. So on the previous escape route, that's why it's in light gray. You can, it can still be seen. We just looked at expansion consistency, for instance, beta plus here. Then we characterized the top cycle. Gamma was a weaker condition. Gamma is also implied by rationalizability, because rationalizability is equivalent to alpha and gamma. And now on this new escape route, because of this statement here, so we have this intermediate notion of rationalizability called quasi-transitive rationalizability that implies stability. Okay, and this implication directly follows from this here, because this condition implies alpha, alpha hat, and gamma hat. So it in particular implies alpha hat and gamma hat, which is stability. And of course, set rationalizability is weaker than stability, because set rationalizability, according to this statement here, is just alpha hat. Okay, so this here is alpha hat and gamma hat, and this here is just alpha hat. And now the idea for this escape route is to look at or to search for social choice functions that satisfy any of these conditions. And it will turn out that the functions that we are, well, as I said, we are basically only discussing one, even though there are more of them. But virtually all of the functions that satisfy set rationalizability also satisfy stability. So the nice thing is we are able to find functions that satisfy this relatively strong notion called stability. Okay. And that's precisely what we are doing now. So let's check for some functions whether they are set rationalizable. So whether they at least satisfy this alpha hat condition. Because whether a function is set rationalizable can be easily checked by just checking whether removing losing alternatives doesn't affect the choice set. Okay, so it should not be the case for, if you now turn from choice functions to social choice functions, that we have a voting rule which selects a set of winners, and then if we delete one of the losers, then the set of winners suddenly changes. So it turns out that this condition is rather demanding, this alpha hat condition, because all non-trivial monotonic scoring rules, for example, violate alpha hat. And this can be seen by the following relatively simple preference profile. So here we have 6 voters and 3 alternatives. And let's just do it for, so this example is quite universal. It works for all voting rules, and it also for all scoring rules, but it also works for a number of other social choice functions. Let's just look at this profile from the perspective of plurality, because that's usually quite easy. So if we look at plurality, then the winner would be alternative A, right? And if we are now deleting one of the losing alternatives, say alternative C, which is not selected, then there are 3 voters who prefer B the most, and 3 voters who prefer A the most, and therefore the choice set would be AB, right? And that is already a violation of alpha hat. The winner set was A, now we are deleting a loser, and then the winner set is different than it was before. So you might think, okay, so it's only a slight violation because here we have a plurality tie, but you can find more drastic examples. So the nice thing about this example is just that it's very universal and works not only for plurality, but for any other scoring rule as well. And the funny thing is that this failure of alpha hat is not only a special feature of scoring rules, but it really holds for many functions defined in this course. So in the first lecture, we had instant runoff, plurality with runoff. Then we also, at one point, we discussed Baldwin's rule, which is this iterative rule where we delete alternatives with the lowest border score. Black's rule, even Kameni's rule, so which otherwise had some nice properties. But here, remember again that Kameni's rule really has these nice properties as a social preference function, which returns rankings of alternatives. So then it also satisfies this reinforcement condition. But if you only look at the Kameni winners, then the properties of Kameni's rule are not as nice anymore. Maximin, Young's rule, Copeland's rule, even the uncovered set and the bank set, so social choice functions that we have studied on the previous escape route, they all violate alpha hat. Okay, so that already narrows down the choice of functions that could possibly satisfy this alpha hat condition. Now, if you think about the definition of alpha hat, so it just says deleting an alternative doesn't affect the choice set. Perhaps I even mentioned it when we were discussing a particular function. Do you have any idea which function, which is not mentioned there obviously, does satisfy alpha hat? So a function where deleting a losing alternative from the feasible set doesn't affect the set of winners at all? Yes? Yes, yes, the top cycle. So I'm not sure. So did you get it why it's not listed here? Or Exactly, right. So if you think back about the definition of the top cycle, it's a minimal dominant set. So everything in the set dominates everything outside. Otherwise, we don't have any conditions. If we delete losing alternatives, well, then a dominant set is still a dominant set. And the only thing that we need to check is whether there's no smaller dominant set now, because that would also change the top cycle. But you can easily verify, like if you write down the argument, it's maybe only 1 or 2 lines, but deleting losers cannot yield a smaller dominant set. So therefore, the top cycle indeed is an example of a function that satisfies alpha hat. But otherwise, I don't know whether, regarding all the functions that we have discussed here, I'm not sure whether any of the other ones, well, of course, trif, the function that always returns everything, that satisfies alpha hat as well. If you delete losing alternatives, the choice set is not affected, because you cannot even delete losing alternatives. But it's not really interesting, the trif, so, but top cycle is, so it's nice to see that we have at least one function from the ones that we have studied so far that satisfies not only alpha hat, so that means it's set rationalizable. We only talked about alpha hat so far, but it also satisfies gamma hat. And also verifying gamma hat for the top cycle is not too difficult, right? So if you think about one tournament where there is a top cycle, and then you have another tournament which is overlapping with the original one and is the very same top cycle, then of course this set will also be a dominant set in the union of these two tournaments. And there also can be no smaller dominant set, and this is like a simple argument to show that gamma hat is satisfied as well. So this is our first positive example of functions that satisfy alpha hat and gamma hat. Okay. Now, as I said, so there's few other functions that also satisfy this alpha hat condition, but in the rest of the lecture I will completely focus on a function called the bipartisan set. The reason why it's called the bipartisan set I will mention maybe, I don't know, 20 minutes from now or something, because it's not completely obvious. It has something to do with game theory, which at this point is not clear, but maybe just let me first just introduce how this function is defined, and then hopefully you get some more intuition into that. So in order to define the bipartisan set, just like for the top cycle and the uncovered set and the bank set and tournament equilibrium set, we need some auxiliary notion. And what we are doing now for the bipartisan set is we are introducing a probability distribution over the alternative. So this is something that we haven't done before, but this will be used in order to define the bipartisan set. Nevertheless, the function will not be probabilistic or anything like that. So in the end, it's just a regular majoritarian function that for every tournament gives us a subset of vertices, not a distribution over the vertices. It can be interpreted like that. We will do this, I guess, 2 weeks from now. But at this point, this is just an auxiliary concept that we need. So we have a probability distribution P, which attaches to every alternative some probability. So probabilities, what I mean by probability distribution here is that these numbers are between 0 and 1, as it is stated here. And of course, they add up to 1. Okay, so that's why it's a probability distribution. In economics, probability distributions are usually called lotteries. I will use this term too, mainly because it's much shorter than probability distribution. And yeah, right. So that's what we have so far. So P can be an arbitrary distribution. And then we are going to define the value of a vertex in this tournament, or an alternative, with respect to a probability distribution P. So Vp of x is just all the probability that we put on the dominators of x minus the probability that we put on the dominion of x. Okay, so this is the value of alternative x with respect to the distribution P. So at this point, you only need to know that this is clearly a well-defined concept. Maybe to get some more insight, let me try to draw an example here. So let's say we have, okay, 3 alternatives, A, B, C. Now, since we are going to talk about majoritarian functions, these will form a tournament, and for simplicity, it's always nice to first look at a 3 cycle, for example. And then we have this probability distribution P, which I will mark in green here, which attaches a probability to each of these alternatives. At this point, I don't say where this probability comes from. We can take any distribution. So for instance, let's say we put 0.6 on A, 0.3 on B, and 0.1 on C. And now we can define the value of each of these vertices with respect to this distribution. Okay, and those I will write down in red. Okay, let's first look at A. Just looking at the definition, what would be the value of A with respect to this lottery P? Excuse me? Yes, minus 0.2, exactly, because we have to look at the dominators of A, and the accumulated probability for the dominators, it's only a single one here, is 0.1, and then the probability of the dominion, that's 0.3, so we have 0.1 minus 0.3, and that gives minus 0.2. Okay, so the red number, maybe let me also, so the green numbers are P, and the red numbers are V P of X. Okay. Well then, this is P of X. Okay, how about B? So what would be the value of B regarding this green lottery? Yes, 0.5. And C? Yes, minus 0.3. Okay, so at this point I'm just playing around with numbers. It's not clear why these numbers are meaningful, but I want to make sure that all of you understand how these numbers are computed. Okay, so here you can see that once we have such a probability distribution, we can assign these values to the different alternatives. And now the idea that we want to follow is that we want to find a distribution over the alternatives that performs well against all the alternatives. Okay, and how well a distribution performs against an alternative is reflected in the value. So for instance, if you look at this example here, so this distribution, this green distribution, performs well against alternative B. The value is 0.5, so the highest value here, because with high probability it picks an alternative that is better than B. Okay, and only with low probability it picks an alternative that is worse than B. Okay, so this is the intuition for defining the values like this. So we want to have a distribution that is more likely to pick a better alternative than a worse alternative. So for instance, the same distribution doesn't do very well against alternative C, so here the value is minus 0.3. If this number here is negative, it means that we are more likely to pick a better alternative, a worse alternative than a better alternative. Right? So if you look at the comparison between C and this lottery, the lottery will pick a worse alternative with higher probability than a better alternative. That's why this number is negative here. Okay, so in general, we want to define lotteries that perform well against all the alternatives. So here, this lottery performs well against one of the alternatives, but not against all of these. Okay, so maybe at this point, let's think about maybe can we find a different lottery here, which at least makes sure that the probability that the randomly chosen alternatives is better than any given alternative, that this event is more likely than picking a worse alternative. So can we find a lottery P such that for every alternative X, we are more likely to pick a better, we are at least as likely to pick a better alternative than a worse alternative. So we cannot find a lottery which always picks a better thing, but can we find a different lottery for which at least we don't have the probability of selecting something worse should not be higher than the probability of picking something better? Yes? Exactly, right? So if we assign probabilities 1/3, 1/3, 1/3 to all these three alternatives, well, then we are not doing exceedingly well, but at least we are not doing bad in the sense, so that the probability that we find something better is always exactly the same probability that we pick something worse from the other alternatives. And also, if you think about this simple tournament here, so it's the Condorcet cycle, and we know that, well, we cannot really do much better than, in this case, since we have random selection here, to uniformly select one of the alternatives, or that all three of these alternatives are equally good. So one thing that we need to realize first is that for every lottery P, so no matter which lottery it is, there always exists some alternative for which the value is non-negative. Okay, so in the example here on the right-hand side, for instance, so the values are the red numbers. We had alternative B, and there the value clearly is non-negative. And this exists in general. So so no matter what the lottery is, so even if we define it in a very bad way, there will be at least one alternative against which this lottery achieves a value of at least 0. Okay, and this is not shouldn't be completely surprising. So it's somewhat related to this handshaking lemma that you may know from graph theory. So let me show you the proof for this statement here. So yeah, it looks quite mathematical, but it's rather simple. So the important idea is that you need to know how you start here. So what we are doing here is we are looking at the sum of all these values which are weighted by the probability of the same alternative. Okay, so maybe at this point it's not clear why we chose this. To just accept that we just want to expand this sum here. Okay, so for every alternative we look at the value times the probability. Okay, so we could also do this in the example here on the right hand side. Then we just multiply the red and the green numbers here. Okay, so now the value of an alternative is defined as follows here. Okay, so the only thing that I did from here to here is just that I've replaced VP of x with this difference here of these two sums. So this is precisely just the definition. Okay, and now we know that in tournaments, and so all these y's that we here are looking at, so either they are in the dominators of x, they are in the dominion of x, and the only remaining possibility for y here would be x itself. Right? So we can just partition any tournament into three parts: the dominators of x, the dominion of x, and y itself. And using this, we can just rewrite this as a sum where we have two variables, both x and y. And now y goes over all these different alternatives. And depending on which y we have taken, we are multiplying the positive probability py or the negative of the probability of y. And which one we take? Well, it depends on the sign of this value here, right? So this is just, so we have to make sure whether y is dominating x or whether x is dominating y. And this we can just tell by looking at this term here. Okay, if the number of voters who prefer y to x minus the number of voters who prefer x to y, so if the sign of this is positive, then there are more voters, then we have an edge from y to x in the majority graph. And otherwise we have an edge from x to y in the majority graph. So that means if this thing here is positive, we are in this part here, and then we just take the positive of py. And if this thing here is negative, we are in this part here, so we have to take the negative of py, and then the sign also becomes negative, so that's fine. The only missing part that is not explicitly stated here is just that if y is exactly x, and if y and x are the same thing, well, then this will be 0 here, and we are just adding another 0, so which doesn't make a difference. Okay, so this is really just arithmetic that brings us from this thing here to this thing here. And now, hopefully, it's relatively obvious that this sum here has to result in 0, right? Because we have two variables, x and y, and then the terms that we are summing up are completely symmetric with respect to x and y. So once one time we take x and y like this here, and then if we, for instance, exchange x and y, then we have exactly the same term with a negative sign. Okay, so and that means that the sum of all of these terms here has to result in a 0 in the end. Okay, and as an implication from this thing here, we clearly also get that there has to be some alternative for which the value is non-negative, because if the sum if this sum here, so maybe let me highlight the important parts here. So we have shown that this sum here is 0. Well, then of course, since the probabilities are always non-negative, we have to make sure it has to be the case that at least one of these VP x's is greater or equal than 0. So it is impossible that all of them are negative, because otherwise the sum couldn't be 0. Okay. Okay. So we have. So that means that any lottery, no matter how bad the lottery is, it will always, at least for some alternative, give us a positive value. Okay. So far, so good. So now we know how to work with these distributions, these lotteries, and these values. Now the question is, so what kind of distribution do we want to find? And now we say that a distribution is optimal, or this lottery P is optimal, if VP of x is greater or equal than 0 for all x's. Okay, so this is something that would be really nice, because these values describe how good a lottery does against a given alternative. And if VP of x is greater or equal than 0 for all the alternatives, it just means that the lottery does reasonably well against all the other alternatives. So it doesn't lose more frequently than it does win for any of the alternatives. And that, of course, is something that we would like to have. For instance, when I ask you about a good lottery for this example here, for this 3 cycle, so you said that 1/3, 1/3, 1/3 would be good. And this lottery, for instance, precisely has this property here, right? So in this example that you gave, it's exactly 0 for all the alternatives. But of course, there could be other ones where sometimes it's even positive. And the reason why we think that these distributions are really good distributions is that the alternative selected by P is at least as likely to dominate X than to be dominated by X. Okay, so this is precisely what we are stating here by saying that these values should be greater or equal than 0. So in other words, such a lottery P represents something that could be called a randomized weak Condorcet winner, because this lottery P here, so note that this is not an alternative, it's a lottery over the alternatives, beats or ties every other alternative that is given in this tournament. Okay, so if we can find a lottery that is optimal, it's quite nice, because in expectation, it beats or ties all the other alternatives, which is something that would be desirable. Okay. Now, the interesting question, of course, that we have now, that we face now, is that, okay, in the simple 3 cycle example, we know that an optimal lottery exists, but does it exist in general? So is it possible that there are tournaments for which there is no optimal lottery? And even if someone is guaranteed to exist, maybe there are several of those, and it's not clear which one to pick. And this is precisely where the main theorem of today's lecture kicks in, and that's a theorem by 3 Frenchmen, Lafont, Lallier, and Le Breton, and they have shown that every tournament admits a unique optimal probability distribution. Okay, so we get both existence and uniqueness at the same time, which is quite nice. So not only does such a lottery always exist, which is far from obvious, it's even unique, which makes this statement much nicer. And there's a second set of authors given here, because independently 2 mathematicians, so these are economists here, so these 3 authors here are economists, and independently 2 mathematicians proved basically the same statement in a paper on tournament graphs. So this is just a graph theory paper, which wasn't really concerned with social choice very much, but they prove exactly the same statement here. Okay. The existence of these optimal lotteries follows from the minimax theorem. And some of you may have heard about this theorem. For instance, we have been using it in the game theory class. But the nice thing is that relatively recently I found a proof in the literature which can be used to prove the minimax theorem much more easily than the traditional proofs. So most of these traditional proofs use things like fixed point theorems or separating hyperplane arguments and rather complicated mathematical arguments. But the nice thing is that I'm able to show you a simple proof by induction, which proves the existence of optimal probability distributions. Now I'm a bit torn, but I think so this proof consists of 2 things, existence and uniqueness, but I think so let's do the existence proof, and then let's look at the uniqueness after the break. Okay, but the fact that we are going to show is hopefully clear enough, right? So we want to show that every tournament admits a lottery that is optimal, so that guarantees a value of at least 0 for all the alternatives. Okay, and as I said, so this proof works by induction. So I don't think we have seen many induction proofs in this course here, but it works on induction on the number of alternatives. Okay, so we first start with a singleton tournament, where like in most induction proofs, so the induction basis is very easy, and then we work ourselves forward to tournaments with more than one vertex. Okay, so it's a proof by induction on the number of alternatives in the feasible set. Okay, and we start with the base case. Okay, in the base case, the feasible set consists only of a single alternative. And then what we need to show that there is an optimal distribution there. Okay, so, well, if you have only a single alternative, there is only one distribution. We put all probability 1 on the single alternative. And then this distribution is optimal if it guarantees a non-negative value according to this distribution. Okay, so if you think back about the definition of a value, we need to look back at the dominators and the dominion of x, but both of these are empty, and therefore clearly the value is just 0, and that proves the statement. Okay, so this here is very simple because both the dominators and the dominion of x are the empty set. Okay. Now, more interestingly, we now have an induction step. By the way, just a general statement about induction proof. So later in this course, I think even next week, we sometimes have statements where the induction step is very easy. It can be shown very easily, but the induction basis is really, really difficult. That's usually the case when the induction basis starts later, not just at a single alternative, but maybe at 5, 7, or 9 alternatives. So you don't have to take for granted that it's always the induction step that is the difficult part. It can also be the other way around. Okay, so for the induction step, we now define a lottery P. Okay, we want to show that an optimal lottery exists. So we cannot assume that P is an optimal lottery. That's what we want to show. So we now define a lottery P as follows. It's the lottery that maximizes the minimum value of any of the vertices. Okay, let me first write down what I mean here. So the minimum is taking over all the vertices, and then the maximum is just taking over the set of all probability distributions. Okay, so we are mapping any alternative to a probability between 0 and 1. So in other words, we are defining a lottery which maximizes the minimum value. Okay, so a lottery like this has to exist. So for the mathematicians among you in general, these terms do not always have to exist. But yeah, here it follows from the fact, I'm not writing it down here because this VP of x function is linear and bounded, and therefore such a max-min term always has to exist. So it's just, so we don't know whether an optimal lottery exists, so we look at a lottery that does as good as possible. Okay, so for which the worst value is still very large. And now we assume for contradiction. So within this induction step, we have a contradiction. That what this lottery achieves is not that the value of all the alternatives is greater or equal than 0. So it only achieves something less. Okay, so the minimum value that it achieves is something negative. So the minimum that this lottery achieves is some number that we are defining now to be the minimum value according to this lottery, so V min. And by this assumption which we make for contradiction, it's something less than 0. Okay, Okay, and if we now get a contradiction, so then we have shown the entire statement, because then the assumption was false, and that means there doesn't exist such a lottery. So that means any such lottery has to give a value that is strictly positive, is non-negative. But now we assume that the only thing that we can get is something negative. Okay, now we are basically using two statements in order to define a new lottery, which will then result in a contradiction. So the way this proof works is that we are now constructing a new lottery which is different from P, and this lottery will give us a guaranteed higher value than this V min value, and therefore we have a contradiction. And there are two building blocks that we need in order to construct this lottery. Well, the first one is, of course, the induction basis. So we know that for a smaller tournament, which has one alternative less, we will have always an optimal lottery. So we can take this optimal lottery from the smaller tournament. That's the induction hypothesis. And then the other thing that we need is what we showed on the slide before. So we showed that for any lottery P, there is some alternative for which the value is non-negative. Okay, so that was what I showed you using this chain of equations and all these sums. So let me just repeat the statement here then. So we know that there is some alternative Z such that the value of Z according to this lottery is at least 0. Okay, and these two building blocks, so I said the induction hypothesis and the single alternative taken together allow us to exactly derive a contradiction. Because if we want to use the induction hypothesis at this point, we don't know. So we know that in any smaller tournament there is always an optimal lottery, and but we don't know to look at which smaller tournament. And here we know that there is some alternative for which the value is already non-negative. So we take this alternative, we look at the tournament except alternative Z, and then we know that the smaller tournament already has an optimal lottery. Okay, and then we are constructing a new lottery by mixing two lotteries in order to derive a contradiction. So this is the idea of what follows. Okay, so let's maybe highlight here to make this look at least a bit nicer. So here we have the induction step, the base case. And now we know by the induction hypothesis that every smaller tournament has an optimal lottery. In particular, the smaller tournament which we get if we only omit alternative Z. Okay, so that means there is some lottery Q, which is now the optimal lottery for the smaller tournament. So it's a lottery. So here we have defined this lottery on all alternatives in A, even though we are removing Z now. So that means that Q of Z has to be 0. And for all alternatives X different from Z, we know that the value of this lottery with respect to alternative X is greater or equal than 0. Okay, so what I've just written down is that we take Q is an optimal lottery in this smaller tournament where alternative Z was thrown out. Okay, now we are almost there, because once we have these two things, we can define a new lottery R. Okay, so we now have two lotteries. We have lottery P and we have lottery Q. Okay, so we know that lottery P only achieves a negative value. So if you look at all the different alternatives, so even the best it achieves is just a negative value. Then we have lottery Q, which achieves a non-negative value for all alternatives except alternative Z. And now the way how we are defining lottery R is just that we are mixing the lotteries P and Q. So we take the convex combination of P and Q. So we're taking a lot of P and only a little bit Q. Okay, so we mix it with the ratio 1 minus epsilon and epsilon. So we put most probability on P, which is the lottery that only achieves this negative value here. Then we put in a tiny probability on the lottery Q. And by doing this, we can make sure if we make epsilon small enough, that we can get a higher value than V min. And that is already a contradiction, and therefore we are done. Okay, so we are not trying to find an optimal lottery or something. We only want to find a lottery that does better than P, because then we have a contradiction. So once we have contradicted the star statement, we are finished. And that's why we are mixing these two lotteries in a specific ratio. So R is defined as 1 minus epsilon P plus epsilon Q. At this point, I'm not specifying what epsilon is. So in the end, we will argue that it just has to be small enough. So at this point, R, for every epsilon, we have a different lottery R. But in the end, we will just make epsilon very small in order to achieve what we want to have. OK, now if we define R like this, then we can first look at what this lottery, so now we have this lottery R, and we can look at the value that we get from this lottery. So the VR of X, for all the alternatives X, we want to see what are the values achieved by this particular lottery here. And here we basically have to make a case distinction. First, we look at all the alternatives which are different from Z, and then we just look at the single alternative Z. Okay. So for all X that are different from Z, what is the value of lottery R with respect to alternative X? Okay, so what is this? So now we are using the fact that the definition of the values of lotteries, if you have a lottery that is the convex combination of two lotteries, then also the values will be of the particular vertices will be convex combinations of the two lotteries here, because everything there is linear. So that means this lottery, which puts 1 minus epsilon probability on P, with 1 minus epsilon, it will achieve the value of lottery P, okay, for any alternative X. So these could be different values for different alternatives X, but what we know for sure is that the lowest of these values is V min. Okay, so that's why I already wrote greater or equal here, so we can so one thing that we can guarantee is that this value for any alternative X of lottery P here is V min, and V min is a negative number. Okay, and now with some probability epsilon, we are mixing in this lottery Q. Okay, and what is the value that lottery Q achieves on all alternatives that are different from Z? Well, it's always non-negative. Okay, so we now know that with probability epsilon, now I'm a bit confused. Why is it 0? Probability epsilon. Yeah, okay. With probability epsilon, we get this value here, which is non-negative. Okay, so if we only want to have a lower bound here, because we have greater or equal here, we can just take 0, because we know that all these values are greater or equal than 0. And now we are mixing a negative value with 1 minus epsilon, and with the remaining epsilon, we have 0. Okay, and that means that this taken together is definitely something, that is strictly greater than V min, right? Because V min is a negative value, and now we take this negative value with a probability less than 1, and with the remaining probability, we just have 0. So this has to be strictly larger than V min. So that means that this new lottery R gives us, at least for the alternatives that are different from Z, gives us a value that is strictly greater than V min. Okay, and this is no matter how large epsilon is. So in this part of the proof, it doesn't matter whether epsilon is small or not small. So this value that R gives us will definitely be greater than the one than the one that we got from P. Okay, but still, it's not clear that R in general achieves a better values than P does, because we have only looked at the alternatives different from Z. So that is the last case that we still need to check. Okay, so maybe let's here just write end. What is missing now is VR of Z. Okay, and here we again have 1 minus epsilon Vp of Z. Okay, maybe let me first write down everything completely. And epsilon times Vq of Z. Okay, so this is just that I can rewrite the value that we get from a mixture of two lotteries. I can rewrite it as the convex combination of the value that the first lottery gives us and the value that the second lottery gives us. Okay, so what do we know about the value that Z gets according to lottery P? Pardon? Almost? Non-negative, right? Yeah. So we know this is precisely how we have chosen Z. So you're right. So we have chosen Z in the way that this thing here is non-negative. And therefore, of course, also this product here will be non-negative. So maybe let's take red here. So this is greater or equal than 0, which is already pretty good, right? Because what we have achieved so far is just this lottery P. It doesn't do very well, so it only achieves V min, which is a negative number. And now, what do we know about Vq of Z? Okay, so let's see what this is. So Q is an optimal lottery of the smaller tournament in which Z is not contained. And now we want to see what alternative C gets as a value according to this probability distribution Q. And this is almost like a trick question here because we don't know anything about this, right? So it could be very bad, it could be good, but we don't know anything. But even if it's very bad, we can use the fact that we have this convex combination which we can regulate by picking the epsilon in the right way. So this part is already pretty good. So we want to have something that is, in the end, we only want to have something that is greater than V min, which is a negative number. So this part already gives us a non-negative number. And now, no matter what this value here is, we can just pick the epsilon in a very small, we can just pick a very small epsilon such that this convex combination here will give us something that is strictly greater than V min, right? By just making the epsilon small enough. Okay, so we have a non-negative number. I'm also saying positive, so it's a non-negative number. And then we combine it with some other number. So this, for instance, could be as bad as I don't know, -1, for instance. So that's the worst thing I think that can happen. But no matter what it is, if we make epsilon extremely small, so then the combination of these two will give us a number which is also greater than V min. And of course, here we have to add that this holds for small enough epsilon. Whereas in the first line, we had the statement for any epsilon. Okay, you could even specify how small you want to make epsilon. So I think I did it once, but it's not really important here. So it's just, I think, distracting you from what you're actually doing, because the main part here is just to realize that if you make epsilon small enough, so it still needs to be positive, of course. But if you make epsilon small enough, then the value that you get for the vertex Z is strictly greater than V min. And now if we take both of these lines together, then we realize that we have now found a lottery R, which is defined on all alternatives in A. And for all alternatives, including Z, it gives us a value that is strictly greater than V min. But here we assumed that P is defined as the lottery that gives us the highest value possible. So that the lowest value is maximized by this lottery. And the best we can do, apparently here, was to get this negative value V min. But now we have found another lottery which gives us possibly still negative value here. So it will be negative, but a higher value than V min. And therefore we have a contradiction, because we have now shown that the minimum value that X gets in R is greater than V min. And this contradicts the star statement, so this one here. Okay. So what's nice? So this proof fits on one screen here, which is nice because, as I said earlier, so what we have basically shown here is we have proven the minimax theorem, which is an important theorem in game theory that was first proved by John von Neumann in 1928. And all previous proofs of this statement, at least the ones that I was aware of, used some more technical machinery, like for instance fixed point theorem. So von Neumann's proof itself was also rather complicated. It's the main result of his paper from 1928. Whereas this proof here, which is not a proof that I invented, so I found it in a recent textbook, and I think they attributed it to a paper that is actually quite old, from the 50s. But it's, I think, a very nice argument where you can show the minimax theorem without invoking heavy machinery from mathematics. Basically, the only thing that you need to realize here is that you can pick an epsilon which is small enough to make this equation here, inequality here, true. And that really helps in proving the statement. So here we have the induction hypothesis to make sure that this is like a well-defined induction proof that has the three ingredients that you usually have there: base case, induction step, and induction hypothesis. Okay. Other questions regarding this proof? Okay. Then maybe before we have a quick break, let me just reveal, I think, one more bullet. Because I said that this, what we've basically been showing is the minimax theorem from von Neumann. And there's also a strong connection between what we call optimal lotteries here, or optimal distributions, to game theory, because these optimal lotteries and these tournaments here that are given from the majority relation in our case correspond also to the optimal strategies, or Nash equilibrium strategies, sometimes also called max-min strategies in zero-sum games, that you get if you look at the skew adjacency matrix from the tournament. So yeah, so it's just one example here. So if you have like a 3-cycle as we had before, okay, so then you can write down the skew adjacency matrix of this particular tournament, and it will look like this. It only consists of -1s and +1s. Okay, so there's, for instance, there's a +1 here because from, let's say this is A and this is B, because there's a directed edge from A to B. That's why we have a +1 here. And this matrix is skew symmetric, because if we have a positive number here, like +1, we have the negative here, which is -1. And for instance, that means that this 3-cycle here corresponds to this matrix, which in game theory is known as the rock, paper, scissors game, right? Where you have these 3 different possible actions to take. You can pick rock, paper, or scissors, and then you have these cyclical dependencies. So you know that paper beats rock, and scissors beat papers, and so on. And an important question in game theory is whether there's always an optimal strategy for these kinds of games, and this is basically what we have shown here, because optimal lotteries are basically just Nash equilibrium strategies. And that's also, yeah, so the final sentence before the break. So this is also how this name bipartisan set came along. We haven't even defined the set yet, so it's the set of alternatives that get positive probability in the optimal lottery. Okay, so because we want to have a set in the end. And the name comes from the fact that there's also a model of electoral competition where there are 2 parties, and then the alternatives that we traditionally look at, like in a tournament, would be the different points of view that the parties can take. So they can take different positions, and they are in competition with each other, and then an optimal lottery defines an optimal distribution of positions that the parties can take. And because this is a model that only has 2 parties, that's where the name bipartisan set comes from. But in the context that we are looking at this thing, it's not really obvious at all, so you just have to affect that this is called the bipartisan set, but we are not really looking at this electoral competition model. Okay, so the important point that I wanted to make here is just that this is strongly related to game theory. Okay, so then after the break, so we still haven't shown the entire theorem here because we have shown existence but not uniqueness. I'll probably shorten this part a bit, so it's because I don't want to make this lecture too proof heavy. So let's see, maybe I'll skip some parts of the uniqueness proof here, but just note that the other important consequence of this theorem here that there's not only there always exists an optimal lottery, but there's even a unique one, which is pretty cool. Okay, so now let's have a break until 5:45. Before we look at the uniqueness proof, I would like to draw your attention to a consequence of what we have just seen. So we now know that there is always an optimal lottery for any tournament. Now if we go back to this, oops, not that way back, to this statement that we looked at before the break. So I highlighted here that what we are showing here is that this sum here is equal to 0. And now this statement here that I highlighted here holds for any lottery, not only optimal lotteries. But now we know if we assume that P is an optimal lottery, we get an interesting implication here, because here we have a sum of products that has to be equal to 0. And now it turns out that for an optimal lottery, so what I'm writing down now is only for an optimal lottery, is that this thing here is greater or equal than 0, because that's just the definition of optimality. And the probabilities are, of course, also non-negative numbers. And that means we can say something about the alternatives that are in the support of a maximal lottery, so that get positive probability in an optimal lottery. So do you know what we can say about such alternatives, about the value of these alternatives? Yeah. Yes, exactly. So in particular, what I want to point out here is that well, the sum of all these products here has to be 0 in the end. These numbers are just non-negative numbers, so that means if the probability is positive, so if we have something that is in the support of an optimal lottery, so that gets positive probability, then the value of this alternative has to be 0, because otherwise the sum cannot be 0 in the end. And if you think about the simple example that we had with the 3 cycle, that was also the case there. So we had this 1/3, 1/3, 1/3 lottery, and the values of all 3 of these alternatives was 0. And this just is clear now because this follows from this statement here. That's actually something that is quite useful now, because we now know that the value of all the alternatives that are in the support of an optimal lottery has to be exactly 0. Okay, now let me get back to the statement. And look at uniqueness. So it's, as I said, so I'm saving some time now. And I won't explain all the details of this proof, but nevertheless, I decided to at least show you the important parts of this proof, because this is really, as I mentioned before the break, really a crucial statement here. So because once we have established existence and uniqueness of optimal lotteries, then we have a very nicely defined majoritarian social choice function in the sense of the bipartisan set. Okay, so the first part here is just what I've just told you. Okay, so if P is optimal, then we know that any alternative that has positive probability in the lottery P has to have value 0. Okay, so this will be referred to as star later on. And now, since we now have existence, the uniqueness part that remains is just to show that if we assume there are 2 different optimal lotteries, then we get a contradiction. And interestingly, so this is also important, so the existence part works also if we don't have tournaments. So we have this assumption that there are no majority ties that we are making to make things simpler. So we also used it for the top cycle and the uncovered set, so we completely ruled out majority ties. For the existence result, this is not necessary, but for the uniqueness result, this is. So for the uniqueness result, this only works in tournaments. Or in other words, if you think about this game theoretically, so if you think about these optimal strategies for these generalizations of these rock, paper, scissors games, because that's what tournament games are about. Yeah, you always have uniqueness if you don't have any ties. But once you allow ties, so for instance that 2 players can pick 2 symbols and then both of them get a payoff of 0, then uniqueness is not guaranteed anymore. So that's also game theoretically interesting. Anyway, so what we want to show now is that if we assume that there are 2 lotteries P and Q that are different from each other, that are both optimal, we want to derive a contradiction. So I think it's really useful not to write everything down here, because this entire first part here, maybe make it as large as possible, is just about the fact that we can assume without loss of generality that both of these lotteries have the same support. Okay, so the support of a lottery is just the set of alternatives which get positive probability. We are making this assumption because if we have two lotteries which don't have the same support, we can mix them again. Okay, so we have this is why we need a lot of notation here. So we have a mixture of these two lotteries, P and Q, depending on some. So like the epsilon before, now we have lambda 1 and we have lambda 2. We can mix both of these lotteries, and then the consequence is just that we get two lotteries which have the same support if we mix them, because these lambdas are strictly between 0 and 1. And it turns out also that these lotteries are both optimal now. So if we mix two optimal lotteries, then we again get an optimal lottery. Okay, so therefore, from this point on, we will make the simpler to work with assumption that the two lotteries that are supposedly different from each other have exactly the same support. So they only differ in the probabilities that they attach to the different alternatives. Okay? Okay, so and then what we do next is that we define something that is not really a lottery here. So R before was a lottery, but we are defining R of x equals px minus qx for all alternatives in the support. So we are defining something that could be seen as the difference of these two lotteries. Okay, so P and Q are lotteries that assign numbers between 0 and 1 to each of the alternatives, and then we define this R object here, so R of x can be negative, of course, because this difference can be negative. So it's so R of x contains numbers between -1 and +1. So it's like the difference of these two lotteries, P and Q. Okay, and if P and Q are different from each other, then R of x cannot be constantly 0, right? Because these two lotteries have to differ from each other. Okay, and now what we do next is that we write down the value of this R thing here. So strictly speaking, maybe that's not quite clean. So we have defined the value for lotteries, whereas now R is not really a lottery. So it's a difference between two lotteries. So it can even have negative numbers. But if you think about the definition of the value, so you can just take it and even use it for this object, which is not precisely a lottery. So we are just adding all the R values for the dominators and subtracting all the R values for the dominions. Okay, and this is precisely what is being done here. So we look at the dominators. And then these R values, of course, are the difference between, so Py minus Qy. And for the dominions, it's exactly the same thing. And right, so if we just rearrange these terms here, we, of course, get the value for alternative x with respect to P minus the value of x with respect to Q. Okay, so everything, again, just because everything is linear, the value of x is, you could also have written down this directly here, is just the value of x with respect to P minus the value of x with respect to Q. Okay, and now it is claimed here that this has to be 0. And I'm referring to the star statement here now. So everything that is in the support of an optimal lottery gets value 0. Okay, so and these alternatives x here, we are only talking about x's that are in the support of an optimal lottery. So all these values are 0, so these values are 0, so therefore VR of x is 0, okay, for all these x's in B, right? Because these two terms are 0 already. Okay? And so this thing here, so VR of x equals 0, which is highlighted in yellow for all x's, defines a list of linear equations. So VR of x equals 0 for all these different x's. Now we add one more linear equation, namely we look at the sum of all these Rx's. Okay, so note that Rx is defined as it is defined here, and now because of this definition, the sum of all these Rx's has to be 0 as well, right? Because the sum of all these Px's is 1, it's a lottery, and the sum of all these Qx's is also 1, so therefore the sum of all these Rx's has to be 1 minus 1, which is 0. Okay? So we have this list of linear equations, another linear equation, and therefore 1 and 2 taken together define a homogeneous system of linear equations with integer coefficients. So you need a tiny bit of linear algebra for this proof, but not really very much. So homogeneous, this means that all these terms are equal to 0 here. And we know that this system of equations has a non-zero solution, namely R. Right? So R satisfies these conditions, and we said earlier that these two lotteries P and Q are different from each other, therefore R cannot be constantly zero, so it has to be a non-zero solution. Okay, so this system of equations defined here has a solution that is different from zero, and since these equations only involve integer numbers, so there are no rational numbers involved here, we can also find a solution which only uses integer numbers. Okay, because this is basically just something that is a basic fact from linear algebra that you need to understand. So if you have but it is also quite intuitive, I think, even if you're not familiar with that statement. So if you have a system of linear equations and all of these equations only use integer coefficients and the system has a solution, then it also has to have a solution only using integer numbers. Okay, and then we take now R star, which is a solution to the system using only integer numbers. Okay, so R, the solution R that we had before, consisted of fractions. So numbers. So R was defined using numbers between -1 and +1. And now we can also take a larger solution, which is R star, that only uses integer numbers. Okay, now we look at this integer solution R star, and we assume without loss of generality that one of these numbers in R star is odd. Okay, so why can we make this assumption here? So why does one of these values that R star attaches to an alternative has to be odd? Well, since this is a system of linear equations, of course we can multiply all these values of the solution by 2 or 10 or something, and then of course, since it's a homogeneous system of linear equations, a solution still remains a solution. Okay, so we have all of these equations here which are equal to 0. And if we have a solution to this set of equations, we can multiply the solution by any factor, and then it still remains a valid solution. Similarly, we can also divide all these solution values by the same number, and it's still a valid solution. So therefore, once we have an integer solution which doesn't have some odd number in it, that means all the numbers are even. So all the numbers that R star assigns to the different alternatives are only even numbers, 2, 6, 10, 12, something like that. Well, we can divide all of these numbers by 2, maybe many times in a row, but at one point, one of these numbers will be odd, right, if we divide long enough. Okay, and the resulting solution is still a solution to the system of equations because it's a homogeneous system of linear equations. Okay, so what we know at this point is that we have a solution to the system of equations, and one of the values that it attaches to some alternative, B here, namely, is an odd number. Okay, now we are almost done, just to let you see that there's not much following here. So in the end, this will be, so there, maybe you have seen proofs like this sometimes before where you which argue about whether a number is odd or even, and this will be one of these proofs, and there are also other proofs about the bipartisan set where this odd-even distinction is exploited. Okay, so one of these values is odd. Okay, now let's look at all these alternatives in the support of these two lotteries P and Q, and therefore also for this difference object R. So first, we know that 0 equals the sum of all these R stars. Well, this is really just this condition here. Okay, so the R star value is just a scaled version of the R. So R is a solution to the system of equations. R star is just a scaled version of that, and therefore this equality clearly has to hold. Okay, now we have the sum of all these different R stars for all alternatives in B. So that means we have, so here at this point, we exploit that we are really talking about tournaments, because I said the statement only works in tournaments. So and when we are exploiting that something is a tournament, I mentioned many times in previous lecture already, a tournament is in some sense characterized by the fact that if we have some alternative X, then we can partition the tournament into X, its dominators and its dominion, and that covers the entire tournament. And that's what we are doing here as well. So we look at all these sums of R stars, so we can take R star of X itself, then we look at all the dominators of X, and then we look at all alternatives in the dominion of X. I just noticed here that this is not very good, so nobody complains. So here, x is now here fixed, and now I'm taking the sum. So x is fixed, and now I'm taking the sum over all x's here. So better take y here. Oops. Sorry about that. Okay, now it makes more sense. Okay, so we can split up this sum into r star of y, r star of the dominators. This should be x, come on. So r star of x, r star of the dominators of x, and r star of the dominion of x. Okay, so and as I said, so this is really where we exploit that this object that we are talking about is a tournament. And now I am claiming that this sum here and this sum here are identical because of this first statement here. So this is referring to statement 1 here. So we know that VR of x is equal to 0, okay, and the value of alternative x with respect to r is all the r's taken for the dominators minus all the r's, or the summed up r's for the dominion, okay. And if the sum of the r's for the dominators and the sum of r's for the dominion add up to 0, that means both of these they don't sum up to. If the difference of these is 0, then both of them have to have the same absolute value. Okay, so that means this is only possible if this sum here and this sum here have exactly the same value here. Okay, so that means we can simplify this statement by just taking twice, say, this term here. We could also take that one because both of them are the same. And this is exactly what I'm doing here. R star of x plus 2 times this sum here. Okay, and now we are almost there at the contradiction, because this here is of course an even number, right? So no matter what these integers here are, if we multiply 2 in the end, it will be an even number. And that means that and in the end, this term here has to be 0, and that means that this also has to be an even number. Right? So it could be that, of course, so it should be the case that one of them is negative or the other one positive. But even for negative numbers, of course, they're even numbers as well. So if this turns out to be 0 and this is even, then this also has to be an even number. And this holds for all x's that are contained in B. So in other words, r star of x is always even. Okay, but this contradicts the fact that r star of this little b alternative here is odd for some alternative b, capital B. And that's where we get the contradiction. Okay, so we assume that there are 2 different lotteries. By simplicity, or for simplicity, we could assume that they have the same supports without loss of generality. Then we constructed this R object here, which is not really a lottery, it's the difference between 2 lotteries. Then we scaled this object here such that it only contains integer numbers. So first, it's not a lottery anymore. It's a difference between 2 lotteries. So there are positive and negative numbers, but these numbers could be fractions. Then we scaled this thing that there are no fractions anymore. There are only positive and negative integers. And then we derived a contradiction by the fact that we had one argument which showed that one of these numbers has to be odd. And then we had another argument down here which showed that all of these numbers have to be even. And that's just simply not possible. And therefore, our initial assumption, which we made in the beginning, that there are 2 different optimal lotteries, was incorrect. Okay, so I'm aware of the fact that this, maybe both of the proofs that we had today are probably a bit more demanding than the ones that we had before. But still, I think just if you look at the length of the entire proof, so it's still like digestible in a reasonable amount of time. Okay, so unless there are questions regarding this theorem. So if some questions pop up later, which with these proofs I can easily imagine that only maybe tomorrow or the day after tomorrow you have some questions, you can just ask in the forum, and then either I or some of the tutors will try our best to answer your questions. But now both of these statements taken together show that not only do we always have an optimal lottery, but there's even a unique such lottery. And now the missing part now in order to really get a majoritarian social choice function is to define this function. So the bipartisan set of a tournament is given as the set of all the alternatives that get positive probability in this unique optimal lottery. Okay. I'm going to show you some examples for the bipartisan set, in particular for optimal lotteries. Okay. Now, interestingly, so there are some further facts that can be derived for these optimal distributions that have immediate consequences for optimal lotteries and also for the bipartisan set. Those can be proven as well. I'm not doing it in this lecture here, but I'm uploading the handwritten proofs of these statements because they're really quite interesting and useful. First one is that if an alternative is in the support of an optimal lottery, so which means it's contained in the bipartisan set, then we have, and there's even an if and only if statement, that the value of this alternative with respect to the lottery has to be exactly 0. So shortly after the break, I showed you one implication of this, but here this actually goes both ways now. So the alternatives, and that also only holds in tournaments. So if you have a lottery that obtains certain values against the other alternatives, it gets exactly 0 against all the alternatives that are under support of the optimal lottery, and against all the other alternatives, it gets a positive value, a strictly positive value. Right? Because the value has to be non-negative, and if it's not 0, it has to be strictly positive. Another curious fact about this thing is that the number of alternatives that are contained in the bipartisan set, and by definition this is the number of alternatives in the support of an optimal lottery, is odd. Okay, for any tournament, there will always be an odd number of alternatives that are contained in the bipartisan set. So there are nice proofs for these statements here, but you can also use it as a tool, because one thing that now that we are completing the entire part about majoritarian social choice functions is that we now can give you tournaments and can ask you to identify the bipartisan set, the top cycle, and the uncovered set of this tournament. And this is something that can be used to verify, for instance, whether your solution is correct. So it's completely impossible that you find a bipartisan set that only consists of 2 alternatives, for instance, or 4 alternatives. So for 2, it's pretty straightforward, right? So if you have 2 alternatives, you can already see that it's impossible that if you have a lottery that only has support size 2, so you attach some probability to x and some to y, but x dominates y, so the value of these 2 alternatives will not be 0. So if the lottery is optimal, at least. Okay, so the number of alternatives in the bipartisan set is always odd. And also these probabilities of optimal lotteries are also odd probabilities. So these numbers are just rational just rational numbers. So they have an numerator and a denominator, and both the numerator and the denominator are odd numbers. So these probabilities that we are working with are, for instance, probabilities like in the simple 3-cycle example, 1/3, 1/3, 1/3, or it could be 3/5 or 7/9 or something like this. But you will never encounter an optimal lottery, at least in tournaments, that is, for which the probability is, for instance, 1/2 or 1/4 or something like this. This is also something that can be used to verify whether you are doing everything correctly. Just to show you that these things can really be shown. So there's basically one unified proof which shows all of these statements, but I'm skipping it here because I'm pretty sure we have had enough proofs for today's lecture. But I'm uploading this one so you can also look at it when you are looking at the lecture material once again. Okay, I guess now would be a good time to look at examples, what the bipartisan set is for specific tournaments. So let's first look at this tournament here. And now the uncovered set, just for comparison of this tournament, consists of 4 alternatives, A, B, C, D. I think we may have even seen this one before. Yeah, I think it's the same tournament we had before as another example, right? So E is covered, and also E doesn't reach some alternative in 2 steps, and that would be alternative A, and therefore A covers E. So the uncovered set is A, B, C, D. And now I am claiming that the unique optimal lottery for this tournament is the one that puts 1/3 on A, 1/3 on B, and 1/3 on C. So in order to check whether a given lottery is optimal, so this can be easily done, we only need to compute the values for all the alternatives. And all these values have to be non-negative numbers. So for instance, if we look at the value of A, what would be the value of A according to these probabilities here? I can actually write down the value in red. So the value of A, so that's the probability that we have on the dominators of A minus the probability that we have on the dominion of A. 0, right? And also it should be 0, right? Because I told you earlier that for everything in the support, the value will be 0. So we could also verify that the values here are 0. Let's look at the perhaps more interesting cases of alternatives that are not in the support of the optimal lottery. So for instance, D here. Okay, so the value of D is, we look at the dominators, 1/3 plus 1/3, that's 2/3, minus the combined probability of the dominion, that's 1/3. So 2/3 minus 1/3, that's 1/3. Okay, and therefore this alternative is not in the bipartisan set. Well, also it gets probability 0 here, so which already made it obvious. And here for E, for instance, it would be again 2/3, and then here in the dominion we also have 1/3, so that's also 1/3. Okay, so the bipartisan set of this tournament consists only of alternatives A, B, C. Fair enough? Okay. So of course, well, at this point I just gave you this optimal lottery, but I'm going to show you later. So in this case, it's not a big secret whether we can efficiently compute the bipartisan set, because maybe some of you have already realized that basically what we have to do is, now that we know that an optimal lottery always exists, we only need to find a probability distribution that guarantees a non-negative value for all the alternatives. And the values are just defined using linear combinations of the probabilities. So therefore, everything that we have to do is solve a linear feasibility program. Okay, so it's like a linear program without a maximization objective. So in some sense, it's even easier than a linear program. So, and that can be done in polynomial time, but I'm going to reveal this later on. But we can find these probabilities in polynomial time. Okay, but now let's look at this other example here. So again, 5 alternatives. Some of these edges have changed, I think. Yeah, not only a single one. Now here the claim is that the bipartisan set consists of all 5 alternatives. And here the probabilities for all the alternatives are not the same. So these 2 alternatives get probability 1/3, the other one only 1/9. All of these taken together, of course, add up to 1, as like any lottery. Maybe let's, as an example, let's look at some of these values here. Well, actually, okay, so since we know they have to be 0 for all the alternatives in the support, we already know what the outcome should be. But for instance, the value of alternative A is 1/3 plus 1/9 minus, because now we look at the dominion, and that's again 1/3 plus 1/9. Okay, so the value of this alternative here is 0. And similarly, the values of all the other alternatives also turn out to be 0. Okay, so some general comments now is one thing that I'm showing you later on, and this will be actually an upcoming exercise, is the reason why this bipartisan set is on this escape route number 4 is because it is set rationalizable. So it satisfies alpha hat, and it also satisfies gamma hat. But alpha hat, as we discussed before the break, is a very convenient property, because it means if we delete unchosen alternatives, then the choice set is not affected. Well, in this example here, there's not really much that we can delete, but in this example here, it means that if we delete E or D or both of them, then the result will not change, and the alternatives in the bipartisan set will always be ABC. And that's pretty convenient. So previously, we have only known that this holds for the top cycle, for example. But the bipartisan set can be shown to be a subset of the top cycle. So, and in practice, it's much, much smaller than the top cycle. So the top cycle had this drawback that it can even return Pareto-dominated alternatives. So the bipartisan set is much smaller, but still has this very nice stability property, which means that we can delete unchosen alternatives and nothing changes at all. What's also possible, which is quite similar, is that if we have some alternatives that are contained in the bipartisan set, we can flip around edges between unchosen alternatives, and the choice set also doesn't change. So it doesn't matter at all what the edges between unchosen alternatives are. So the only thing that is important for what is the bipartisan set are the edges inside of the bipartisan set and the one between inside and outside alternatives. But between losers, we can flip around edges, and the bipartisan set doesn't change. Okay, and also if you think about this definition using optimal lotteries, that's not completely surprising, right? So because they don't play a role here. One other comment is that sometimes people suggest that if you look at this example in particular, rather than taking everything that is in the support of an optimal lottery, rather than that, we could just only take the alternatives with the highest probability, right? For instance, these two here. Maybe if something has a high probability in the optimal lottery, that's also a good indicator that these are good alternatives. And that, of course, would yield a strictly smaller majoritarian function. So it would return less alternatives. However, this function, so it's a well-defined function, so you can define something like this. But this function doesn't satisfy very nice properties. And some of these failures you can already see in this example here. So for instance, if you think about alpha hat, right? This alpha hat property, which says that the choice set doesn't change if we delete losing alternatives. If you pick D and E from this tournament here, alpha hat doesn't hold. Does anybody see why? Exactly, right? So alpha hat for this function, so maybe let me draw what this function does. So it selects D and E. So alpha hat would be violated for a function that satisfies D and E, because as you said, if we delete B and C from the tournament, then we have A, D, and E left. They form a 3-cycle, and from a 3-cycle, every majoritarian function, including the bipartisan set, has to select all 3 of the alternatives. So the choice set was affected by deleting losing alternatives. I was actually thinking about a simpler example, or maybe perhaps simpler example. Yes? Yes. Right. Yes, exactly. Right. We could also delete all of the losing alternatives, and then we would have a function that from this 2-element tournament D and E, where D dominates E, selects both D and E. So that's not even majoritarian. And also, of course, if you look at the definition of optimal lotteries, this is not satisfied if we select D and E here. So one of the reasons why we should not pick the alternatives with maximal probability here is that alpha hat is violated, but there are also other reasons as well. For instance, this function would also violate monotonicity, which is satisfied by the bipartisan set. This is an upcoming homework exercise to show that it is satisfied. So this other function, which only picks the alternatives with maximum probability, doesn't satisfy monotonicity, which is also not so good. By the way, so in general, so I think there are very few functions that can pick 2 alternatives from a tournament. So also the top cycle, the uncovered set, the tournament equilibrium set, and the bipartisan set will never be able to select 2 alternatives. For the bipartisan set, the number of alternatives always has to be odd, so it's straightforward. But for most other functions, it's also not possible. And also, it doesn't really make much sense to select 2 alternatives, because then you say both of these alternatives, D and E, are equally good, but well, D is better than E, right? So the majority prefers D to E. So picking 3 alternatives where there's a 3-cycle between all 3 alternatives makes sense, because all of them are equally good in some sense. But here, picking 2 alternatives such that one is better than the other is a bit counterintuitive. I think Copeland, for instance, can pick 2 alternatives, unsurprisingly. But that's something that is not really a good property, I would say. Okay. Okay. So now let's look at some properties of the bipartisan set. First, there is one more proof, but it's a really simple one, so don't worry about this one. So it's one thing that we would like to know is how the relationship to these other majoritarian functions is, right? So because we had a long list of majoritarian functions, but at this point it's not unclear how the bipartisan set is related to those. I did mention briefly, without any proof, that the bipartisan set is a subset of the top cycle, and that already follows from this statement here. So if the bipartisan set is a subset of the uncovered set, which is a subset of the top cycle, of course, then the bipartisan set also has to be a subset of the top cycle. Yeah, so let me show you the proof of this. As I said, so it's really easy. So we want to show, that's definitely the last proof for today. This time you can trust me. So we want to show that the bipartisan set is a subset of the uncovered set. And for this, so in order to argue at all about the bipartisan set, we need to argue about these optimal lotteries. Okay, so we know that this tournament, whatever it is, has to admit exactly one optimal lottery. So we assume that P is such an optimal lottery. Now, what happens if one alternative covers the other? Right? Because that's what we want to know now. So we have the uncovered set is defined in terms of this covering relation. So if X covers Y, what does this mean for the value of alternatives with respect to this lottery? So maybe not all of you are familiar with the definition of covering, but covering means that everything that is so X covers Y if everything that is dominated by Y is also dominated by X, or equivalently, if everything that dominates X also dominates Y. So in tournaments, these two definitions were equivalent to each other. And if we write them down, you will already realize that this is quite important when we talk about the value of alternatives. So we can say that the dominion of Y is a subset of the dominion of X, and also the dominators of X form a subset, even a strict subset in both of these cases, of the dominators of Y. Okay, and now if we have one probability distribution P, which is fixed, what does this mean for the value of X and the value of Y? Let's have like a little quiz here. So we have fx with respect to P and Vx with respect to P and Vy with respect to P. Okay, so the lottery P remains the same, and the values, we have worked with these the entire lecture today, are just defined by accumulating all the probability that we have on the dominators and then subtracting the probability that we have on the dominions. So what do we then know about these two values? If the only thing that we know about X and Y is that these dominions are contained in each other and the dominators are contained in each other? Yes? Exactly, right? Because we have only extracted, if we go from X to Y, we have only made the dominion smaller and we have made the dominators larger. So there's a direct correspondence if X covers Y between the values of X and Y. And now, in order to show the statement here, we only need to assume that we have, on top of that, so we now have that X covers Y. And if we now assume that Y would be in the bipartisan set, and that means that the probability that Y gets is positive, then not only do we have this weak inequality here, but this equality becomes strict. Okay, because now at this point, so it's still possible that this is that we have equality here. But if Y is in the bipartisan set, then we have positive probability on Y. And since Y is not in the dominion of X and Y is also not in the dominators of X, this equality has to become a strict equality here. So we have VP of X is now strictly less than VP of Y. Okay, and VP of Y, if Y is in the bipartisan set, has to be 0. Right, so just by definition, that's what we have learned earlier. Everything that is in the support of an optimal lottery has to get a value of 0. And that means that the value of X would be less than 0 for an optimal lottery, but that's not possible. Optimal lotteries guarantee a non-negative value for all the alternatives. And therefore, the assumption, so X covering Y is okay, but if Y is in the bipartisan set, it's impossible that X covers Y. And that's exactly the same as saying that everything that is in the bipartisan set has to be uncovered. It's impossible that something in the bipartisan set is covered by some alternative. Okay, so this here contradicts optimality of P. Oh, Okay, there's something missing here. Contradicts optimality of P. And, well, as a consequence, we have that the bipartisan set is always a subset of the uncovered set. And of course, that's also quite useful to know, right? And also, again, for these types of exercises and maybe exam questions, where we give you a tournament and ask you to compute several majoritarian social choice functions. So we haven't really talked about an algorithm for computing the bipartisan set, but I said there is a polynomial time algorithm, but it requires to basically solve a linear program, which is not really something that humans are really good at doing this. But this inclusion here allows you to narrow down the choice of optimal lotteries and therefore also of the bipartisan set by quite a bit. Because if you first, you all know how to compute the uncovered set, and if the uncovered set is already relatively small, let's say it only contains 3 alternatives or something, then computing the bipartisan set also becomes quite easy. In the extreme case, for instance, where the uncovered set is a singleton, you know there has to be a Condorcet winner, and then of course the bipartisan set is also the same singleton, so then things are extremely simple. So you can think of this like a pre-processing step that can be useful for computing a majoritarian function. In the worst case, of course, the uncovered set will be everything, and then you don't get anything from first computing the uncovered set. But usually we're not as evil as that. So if you ask you to compute several majoritarian functions. Okay, so I think this proof is also clear. Great. So we have shown that the bipartisan set is a subset of the uncovered set. And what I also, so otherwise there are no interesting relations known, except for all these statements that follow from this. So for instance, the bipartisan set therefore also has to be a subset of the top cycle. But it turns out that if you also look at random distributions of tournaments, that the bipartisan set selects much smaller choice sets than most of the other, or basically all of the other interesting majoritarian functions do, which also makes it a pretty good majoritarian function. With respect to the Banks set, this is quite puzzling. So it's not known whether the Banks set and the bipartisan set always overlap or whether they can be disjoint for some tournaments. So if you have some spare time and you want to prove something new, this is something you could do. I think we tried it as a Christmas challenge a couple of years ago, but nobody succeeded. Until a couple of years ago, it was not even known whether they can properly overlap. So at that time, people only knew about tournaments where one of them is contained in the other. So either the bipartisan set was contained in the Banks set or the other way around. And then I think in 2015, in our group, we encountered the first tournament using computer search where the bipartisan set and the Banks set properly overlap. And if I'm not mistaken, I think this is precisely the tournament that on last week's exercise sheet you had for the first exercise, where I think the Banks loser exercise. So you can now look at this tournament again and try to compute the bipartisan set, which you didn't know about last week. But in this tournament, the bipartisan set and the Banks set are not contained in each other. But whether they always overlap, nobody knows. Now, the main reason why we are studying the bipartisan set on this escape route is because it satisfies alpha hat and gamma hat. And you're going to show this as an exercise. This may sound difficult, but it's not really that difficult, right? If you think about the definition of optimal lotteries, you know that the optimal lottery is always unique and always exists. Then, for instance, for alpha hat, you only need to think about what happens if we delete unchosen alternatives. How does this affect the optimality of lotteries? Similarly for gamma hat. And also it satisfies monotonicity and even a strengthening of monotonicity that we are going to introduce later on in this course. But here you only need to show standard monotonicity. So these are standard properties that so monotonicity at least is a standard property that functions should satisfy. Satisfying alpha hat and gamma hat is really something quite demanding that is not satisfied by your usual majoritarian function. And with regards to computation, I said that this basically is just a linear feasibility program, and you can even write it down. So if If you just write down the linear feasibility problem, it's really quite short because we are looking for an optimal lottery, P. So all these probabilities only require rational numbers, so we don't even need real numbers here. The values have to be non-negative, and these other constraints only make sure that this is a valid probability distribution. So the numbers need to add up to 1. And they're all non-negative. And then what we return is just the support of the optimal lottery. So this is, as I said earlier, can be seen as a special case of a linear program where we only have linear inequalities, but no maximization or minimization objective. So this can be done in polynomial time, just like linear programming, as hopefully all of you or most of you know, it can be done in polynomial time. However, this problem is also known, in particular also the problem of computing the bipartisan set is known to be p-complete. Has anybody ever heard about this notion? So I'm not saying NP-complete, of course, that would be a bit confusing, but it's p-complete. Has anybody ever heard about p-completeness? Okay, so just like NP-completeness or sigma-2 p-completeness or completeness for any other class, it means that this problem belongs to the hardest problems within the complexity class P. Okay, so of course you cannot use polynomial time reductions there because you have to use types of reductions that are actually less powerful than what the class defines. So you use so-called log space reductions, so algorithms that can only use a logarithmic amount of space. But in other words, so it means, which I think is also quite nice about the bipartisan set, we can compute it efficiently, but it's also non-trivial in the sense that it's just as hard as any problem that can be solved efficiently. And also what p-completeness means is that these types of computational problems cannot be parallelized well. So some problems are so easy that you can easily parallelize them, such, for instance, in some cases they only need a constant amount of time, whereas for solving a linear feasibility program or computing the bipartisan set, this is not possible. Okay, I think there's only one slide left. Yeah, right. So now we have seen lots of good properties of the bipartisan set, but not really convincing characterization like we had for the other functions, for TC, UC, and Banks. We had really nice complete axiomatic characterizations. And the reason why I'm not showing you one is because we don't really know a really good, powerful characterization as the ones that we have for the other majoritarian functions. So we have some partial results, which I'm going to show you, but not really something that is as nice as, say, the characterization of the top cycle using beta plus. And in order to get these statements, one needs to define something that is similar to this refinement condition that we've been using for these other characterizations. So for instance, the top cycle is the finest function that satisfies beta plus in the sense that there are no refinements that satisfy the same axiom. And here we are defining a version which is like a quantitative version of being a refinement. So we say for two majoritarian functions S and S prime that S is more discriminating than S prime if there exists some number of alternatives k such that on average S selects fewer alternatives than S prime on all labeled tournaments of size k. Okay, so this is like a quantitative version because if these refinements things, so many things cannot be compared because they are simply not refinements of another. So for instance, if you compare Banks and BP, so we've seen earlier that there are tournaments where they actually overlap, so none of them is contained in the other. But we could look at all tournaments on, say, 10 vertices, for instance, and check how many alternatives are selected and take the average of all of this. And then we can say, for instance, that the bipartisan set in comparison with the Bank set is more discriminating because it selects less alternatives on average. Okay, so this is how this property is defined, and it allows us to compare tournament solutions in terms of their discriminative power. So here, being discriminating, usually this is a negative connotation, but here discriminating is actually good because you want social choice functions that return small sets of alternatives. So for instance, Copeland's rule is a very discriminating tournament solution. It always returns very small sets of alternatives, but it doesn't satisfy very nice properties. Okay, and then you can prove that there is no discriminating stable majoritarian social choice function than the bipartisan set. Okay, so the bipartisan set is stable. It satisfies alpha hat and gamma hat. And then, of course, a natural question would be, can we find something that also satisfies the same properties and maybe even selects less alternatives on average? And this theorem shows that this is not the case. And a simple consequence of this theorem is also that no refinement of the bipartisan set is stable, right? Because if there is no more discriminating one, there can also be no refinement of the bipartisan set that satisfy these nice properties. So this is why I say there's not really a completely convincing characterization, but we do know that there are no smaller or more discriminating majoritarian functions that satisfy the same nice properties, namely alpha hat and gamma hat. And just recently, a colleague of ours, Klaus Niering, has shown that there's even no majoritarian refinement of the bipartisan set that only satisfies alpha hat. Okay, so stability is alpha hat plus gamma hat, but even if we only take alpha hat, so we cannot find something that is a refinement of the bipartisan set that also satisfies alpha hat. However, we cannot characterize it as the finest majoritarian function, satisfying, say, stability, for instance, because no such social choice function exists. So there is no finest function that satisfies stability. So you can find artificial functions which are not supersets of the bipartisan set, but also satisfy stability. So I think things like these, we also had something similar for the tournament equilibrium set, show you how valuable these statements were for the top cycle and uncovered set and bank set. Just the existence of a finest function that satisfies a given set of axioms is quite nice. So then there is a characterization of the bipartisan set that we have shown a couple of years ago, which uses this most discriminating axiom. So you can say you want to find the most discriminating social choice function that satisfies a given set of properties, and then it uses stability, monotonicity, and two other axioms that I'm not going to define because we haven't studied them in this course. They're called regularity and composition consistency. Regularity is pretty easy to explain. Regularity just means that, so a tournament is regular if all the vertices have the same degree. Okay, so like a 3-cycle, or we have seen these larger tournaments, they are sometimes called cyclones of order 5, 7, or 9, which are completely regular in the sense that all vertices have the same degree. And regularity means that a social choice function in a regular tournament has to select all the alternatives. Okay, so that sounds like it should be satisfied by all functions, but there are some large tournaments which are regular, but which are not completely symmetric. So for instance, the bank's majoritarian function is not regular. So you can find a regular tournament where the bank's winners the bank's winners are not all the alternatives in the tournament. Okay, and for this characterization, one other reason for not naming these other two properties is because we don't know whether they are required. So in some cases, this is also something where you can see how research actually works. So for all the classic theorems like arrow, and some other theorems, we have shown that axioms used in this result are independent from each other. So we had a couple of homework exercises that were of this type where you show that the axioms don't imply each other. For some axioms, this is actually quite difficult to show. And for instance, for this characterization, we don't know whether these additional axioms are required. We can use a computer to show that for up to 7 alternatives, they are not required. But whether this is the case for any larger number of alternatives, we don't know. Okay, so I think that would be everything that we have for today. So that not only concludes this escape route number 4, which only resulted in a single majoritarian function, the bipartisan set. But as I said, so there are also other ones, not only the top cycle, but there's one called the minimal covering set, which also is stable, which we didn't touch here. But it also concludes everything that we did to escape from the Arrovian impossibility. So because in the next lecture, we will start to talk about strategy proofness and also participation incentives. Yes, unless there are any questions regarding the bipartisan